This is a big issue for the flat Earth community, and it's something that we've been sort of kicking around and trying to figure out for a good long while. You have to have a map and you have to have a model.
I challenge you to go through any of my videos and tell me where I'm wrong. Tell me where I'm wrong. Show me proof that the Earth is a globe, and I do not mean a picture from 1972. Show me proof that we are round.
Hello everybody, Steiner here. Welcome to Controversy Central, where we take on controversies that really matter. And here we have a controversy that has become very important to a great number of people. A major theme that we hear from the Flat Earth community has been that of a vigorous challenge to those who are not yet on board to do some serious research of their own before dismissing the idea that the Earth is flat. And some have gone so far as to offer reward money to anyone who can prove that the Earth has curvature or is not stationary. I have taken them up on their challenges, and I'm about to prove that the Earth has curvature. Though the Earth is often referred to as a geoid or an oblate spheroid, and though these terms emphasize certain minor nuances, the general shape of the Earth is that of a sphere. I'd like to thank Zen Garcia for personally challenging me to do my best to prove the Earth is a globe, as you can see him doing here under his Endeavor Freedom icon. So this I now intend to do. I expect that in this and my next two videos, I will be able to show conclusively in two different ways that the Earth has curvature. And the great thing about my evidences is that they are easily reproducible tests that conform to the scientific method. In fact, I seriously considered showing the steps of the scientific method and me applying each step in the process. But I realized that was not required, and that it could become boring very quickly. So instead, I will simply explain what I am doing and allow the data to inform us as to what we observed, and then come up with a conclusion based on the data. Now, as I mentioned earlier, this is the first in a three-part series testing and comparing the globe and flat Earth models. Concerning the flat Earth model, this series will show us that the Earth cannot be flat. It will also show us why the Earth cannot be flat. Concerning the globe model, this series will show that the Earth must be a globe. It will also show why it must be a globe. This series will also show a unique relationship between the globe model and the flat Earth model that can make the flat Earth model useful in a particular way, which I intend to elaborate on in a later video. I started my project with a flat sheet of paper, a globe, some inexpensive items like measuring and marking tools, string, and mounting putty. Then I drew lines of latitude and longitude on the flat sheet of paper. These are the same lines of latitude and longitude as you see on most flat Earth models. In fact, to simplify matters, and since a number of flat earthers are convinced that the Gleason's map is the most accurate map of the flat Earth, I will be using that map for comparison. I will also be showing that those lines and other features that you will be seeing as we proceed are used in the same way on the globe. Those who don't think so highly of Gleason's map will have to bear with me and realize that I am only using Gleason's map for illustrative purposes, not to prove anything. As you can see here, the Gleason's map also uses lines of latitude and longitude. The next thing I did was to mark down the appropriate number of degrees for each line of latitude and longitude, exactly as you see on the Gleason's map. And now, at long last, we can get started with the actual experiment. To perform this experiment, what I decided to do was to find population centers around the world that I could pair up in order to measure the distances between the centers that were paired. Each pair of such centers needed to fulfill certain very specific requirements. For one thing, each pair would need to be separated by approximately the same distance as each other pair. This distance was not arbitrarily chosen. I deliberately went as far south as possible to look for a pair of locations directly east and west of each other that would be as far apart from each other as possible while still not separated by any body of water, such as an ocean, that would make driving between them impossible. This would provide my reference yardstick. All the other pairs of population centers would need to come reasonably close to being that same distance apart. The only landmass that could provide me with two such locations at a sufficient distance apart was Australia, and the two population centers I chose were ones that were about a half a degree either north or south of 32.5 degrees south, so almost directly east and west of each other. These were Perth on the west coast at a latitude of minus 31.950527. For those who don't know, the minus sign here in latitude means south, and Newcastle at minus 32.928271 on the east coast. These figures I found at a website called latlong.net. I also checked to find the distance between them at another great website called distancecalculator.net. That website provides the option of choosing between kilometers, miles, or meters. It gives us both the distance we need to travel if we were driving and the distance we would travel if we were to take the most direct path when flying. Since for my purposes I need to know the shortest distance between 2 points, I will be using the distance traveled by air for my calculations. But also showing the road distances will give us the very best way possible to know that the distances provided by this website are accurate. Since millions of people have traveled along most of these routes, and many have traveled various stretches of these routes a number of times, the numbers we have been given here can and have been tested multiple times by numerous people against the actual distances driven and logged by them, whether they be professional drivers needing to log time and distance on each trip, or others traveling for pleasure or other types of business. You can get a good sample of such satisfied people in their comment section. The actual distance as the crow flies between Perth and Newcastle is 2,088 miles, as you can see on this map. Based on that, I now set about looking for other pairs of population centers that were close to 2,088 miles apart and either directly north and south of each other or directly east and west of each other. That is, as best as possible. I was specifically looking to find one north-south pair and one east-west pair as close to the North Pole as possible, and more of each, north-south and east-west, at distances further and further from the North Pole until reaching the furthest south possible. I wanted them all to be only separated by land. Unfortunately, in order to get one east-west pair as close to the North Pole as possible, I had to choose Volochenka, Russia and Wainwright, Alaska, which are separated by the Bering Strait. I could have omitted this pair, but thought it was important to include them in order to get the most complete picture possible. In this video, I will be plotting only the north-south pairs on both the globe and the flat Earth, and will follow up with the east-west pairs in the next video. If, after I've measured between each pair of locations on the flat Earth model, all the distances are approximately the same, then that model must be accurate for north-south distances. The same holds true for the globe. In case anyone thinks this could get complicated, let me assure you that only some basic arithmetic will be used when we analyze the information that will be collected in this experiment. And another thing, the data that we will be using is woven into the everyday fabric of our lives. For instance, we automatically think of location and distance when our thoughts turn to friends or relatives living at any appreciable distance from us. Location and distance also come to mind when planning a vacation or a multitude of other activities that involve some amount of travel. One of the first things we do when planning a trip is to pull out an old-style map or use digital mapping tools. Many of us go to online websites like latlong.net and distancecalculator.net, check out the links below, to locate our starting point and destination. Then we plot our route, taking note of direction of travel and the distance to be covered. We might even look for other information such as border locations or points of interest along the way. As we start our trip, the odometer in our vehicle automatically begins to log the distance we travel. Along the way, many of us will also check our GPS navigation systems or maps, knowing that the information we are looking for there is accurate for our purposes. An important aspect of the way geographers orient locations on a map with respect to direction and distance is to overlay a grid onto the Earth and use that grid to place locations according to the coordinates provided by the grid. And just as everybody using the English language normally agrees to stick to its conventions to allow clear communication to take place, so everybody using a grid of the Earth generally follows the conventions pertaining to that grid to allow for clear communication of geographic information. For this reason, no one needs to reinvent the grid. We can all clearly and effectively communicate using the very same grid that I see being used regularly on both flat Earth and global Earth models. So let's see what results we get using a string to make my measurements on the globe model. The globe I am using is well made, but could still possibly introduce minor errors into the data, considering the fact that it was mass-produced. This globe tells us that its scale is 1 to 31,680,000. Dividing that number by 63,360, which is the number of inches in a mile, we find that the scale of the globe in terms of miles is 500 miles per inch. The midpoint of the distances I have chosen is 2,096.5 miles. That is 2,112 minus 2,081, as seen here, which equals 31. Divide that by 2 to get 15.5. So 2,081 plus 15.5 gives us 2,096.5. I will round this number up to 2,100, which allows us to come up with a reasonable estimate of how to use the string. Since 1 inch represents 500 miles, we need 2,100 divided by 500, and that gives us 4.2 inches on the string. I've marked out 1 inch segments in red, and immediately after the first 4 1 inch segments, divided that fifth 1 inch segment into 5 2/10 of an inch segments in black. Starting from the northernmost city in each of my pairs, I expect the southernmost city to be reasonably close to the first black mark in the fifth 1 inch segment. Having set the stage, I will now start this segment of the globe test by measuring the distance separating the two north-south locations closest to the North Pole. The end of the string sits at Yellowknife in the Northwest Territories of Canada. This is the city that is the furthest north of the ones we are charting in this video. Then we head straight south to an American city in the state of Arizona, next to the border of Mexico. Its name is Ajo, and on the string we can see that it is 4.3 inches from Yellowknife. Multiplying 500 miles 4.3 times gives us 2,150 miles. DistanceCalculator.net shows the actual distance as 2,082 miles, a difference of 68 miles. Since 1/10 of an inch on the string represents 1/10 times 500, or 50 miles, this 68-mile discrepancy is quite minor. Now we will take a look at the distance between the same two cities as we plot them on the flat Earth model. Since for my purposes I do not need the precision achieved by the coordinates provided by latlong.net, I will round the numbers off in order to simplify the process and make it a little easier on myself. So everybody using a grid of the Earth generally follows the conventions pertaining to that grid to allow for clear communication of geographic information. For this reason, no one needs to reinvent the grid. We can all clearly and effectively communicate using the very same grid that I see being used regularly on both flat Earth and global Earth models. So to begin, we will go to a website that gives us coordinates in terms of latitude and longitude. And there we will find the coordinates of the North American cities of Yellowknife, Canada and Ajo, USA. For Yellowknife, they are 62.5 degrees north and 114.4 degrees west, while for Ajo, they are 32.4 degrees north and 112.9 degrees west. Plotting them on the flat Earth grid places Yellowknife here and Ajo here. The distance measures out as approximately 2.4 inches. To see how accurate the flat Earth model is for distances north and south of each other, we now need 4 additional pieces of information. The first is the distance from the North Pole to the equator. A quick search online will show that distance to be approximately 6,215 miles. This is the most important distance I know of that is generally accepted by both the flat Earth and global Earth communities, and that can, as well, be used as a starting off point for comparison and testing. The second piece of information that we need is this same distance as it is portrayed on my grid. My ruler shows that to be approximately 7.06 inches. Dividing 6,215 miles by 7.06 inches gives us a third piece of information we need. This is the number 880, which tells us that each inch on the graph represents approximately 880 miles. This allows us to calculate that the actual distance between Yellowknife and Ajo, as represented by my grid, is 2.4 times 880, or 2,112 miles. All the travel distances I will be using are the shortest, most direct routes possible. They are the routes that would be used if we could drive the total distance in one straight line. In other words, as the crow, and usually the aircraft, flies. The actual route by road can sometimes be much longer, as the roads turn here and there to avoid various obstacles. I have specifically chosen to use distancecalculator.net so we can see both the direct and the meandering routes. That allows for a direct visual comparison. Above the map, you can also see, next to an airplane icon, the mileage of the shortest route, and next to it, a car icon with the best road distance. As you will see, for each pair of cities, the distance traveled by car is always much greater than the distance that is flown by an airplane when it follows the shortest route. Knowing that distancecalculator.net gave the actual mileage as 2,082, while I had measured 2,012 on my flat Earth grid, we have a negligible difference of 2,112 minus 2,082, or 30 miles. To see how insignificant that is, all we need to do is take the 880 miles that are represented by 1 inch and divide that number by 16 to get 55 miles. In other words, the 30-mile discrepancy represents less than 1/16 of an inch on my grid. The flat Earth model works spectacularly for north-south distances, and my hand-drawn grid has given an amazingly accurate result. That was interesting, but let's try this a couple of more times, just to make sure that it holds true for north-south distances elsewhere. The first is Algiers, in Algeria, to the north of the continent. The second is a port in the Gulf of Guinea by the name of Lagos, Nigeria. The measurement is very accurate at 4.2 inches or 2,100 miles compared to 2,088 miles at distancecalculator.net, a difference of 9 miles. Now it's time to get back to the flat Earth model and chart the same two cities there. Again, the distance on my flat Earth grid is 2.4 inches, yielding the same 2,112 miles as between Yellowknife and Aho, while the actual distance as provided by distancecalculator.net is 2,091 miles. So again, the difference is negligible, a mere 21 miles. I have one more north-south pair of locations to chart. The first is the city of Bukavu, just south of the equator in the Dominican Republic of the Congo. The second is a port city by the Indian Ocean on the southeast coast of the continent of Africa, in the country of South Africa. Its name is East London. On the string, it appears to be about 4.3 inches from Bukavu to the north. This works out to a distance of 4.3 times 500 miles, or 2,150 miles. Distancecalculator.net gives the actual distance as 2,112 miles, a difference of 38 miles. And now I will complete the series of tests on this video by plotting the distance between these same two cities on my flat Earth model. The distance on my grid is again 2.4 inches. Since the actual distance as provided by distancecalculator.net is 2,112 miles, we have no perceptible variance whatsoever. And that once again yields 2,112 miles. This means that whether in the far north, near the equator, or far south of the equator, the distances measured between locations that are north and south of each other are accurate on the flat Earth model. So what are we to make of all this? First, let's take a close look at the results as I've laid them out on these charts. And the results are actually very interesting. You'll note that I chose 3 pairs of cities at locations strategically placed to ensure that I had a sampling that spanned a good portion of the Earth, starting at Yellowknife, Canada, which is fairly close to the Arctic Circle, and ending at East London, near the southern tip of the African continent. When looking at a graph of the results, we find that the globe model closely paralleled the distances we were given on distancecalculator.net. Here on the graph, we find that the largest discrepancy distance-wise is 68 miles. As we saw earlier, that represents a stretch on the globe model slightly over 1/10 of an inch. In comparison to the overall distance, this amount is clearly insignificant and showed a much greater accuracy than I actually expected, considering the tremendous scale reduction. On the flat Earth model, the greatest discrepancy was 30 miles. So again, given the scale of the model, I was surprised at such accuracy. 30 miles represents less than 1/16 of an inch on my handmade flat Earth grid. This means that the test I used for this first round clearly has not resolved the question we started out with, namely, which model, if either one of the two, is the accurate one? So I will now need to produce and upload my next video to reveal the results of the second match between these two models. Are the globe and flat Earth models both accurate again as I test them for east-west distances? To learn what the results of the next and maybe final face-off between these two models of the Earth reveal, be sure to click on the subscribe button below and then the notification bell. This way you will be notified as soon as I post it online, which should be within the next few days. Until then, thanks for watching.